In this video, we're talking hypothesis testing for a population mean mu, but we're not going to have population information. So it's going to require us to use a t-test or to use a test statistic t. Let's dive into our arguments. We're going to talk about an introduction to what is this t-test or t-statistic. We're going to then go through some examples building out exactly that test, forming the hypotheses, building that p-value, and then making a decision. Let's get into it. Previously, when we conducted these hypothesis testing for the population mean, we knew the population standard deviation. Again, a nice little example would be the population standard deviation is 4. We knew the spread, not of just the sample we collected, but the population altogether. And this allowed us to use a z-test, which gives us the best or the better p-value. In this section, though, we're going to conduct these hypothesis tests, but without population standard deviation. And there's actually a really good reason for this. In practice, we often assume that the population standard deviation is unknown because, again, the whole point of hypothesis testing is to show or to prove our claim, or we're asserting that the population mean is wrong. Again, there's 3 kinds of changes: not equal to, less than, or greater than. And so if we're trying to prove that the population mean is wrong, then it might be improper, especially how far that mean may be off, to use the population standard deviation, because that also might be way off. And so to that end, we cannot rely on a population standard deviation to conduct our test, in which case it's t-test to the rescue to build that p-value out in a way that doesn't rely on the population standard deviation. T-test is often used as well for small sample sizes, that if you have a small group and you can't rely on population standard deviation, t-test will give you a more accurate p-value. Let's dive into the specifics before we start doing some examples. So again, we have this Z and T test business. Z test being the better test between the two if you can choose, but it relies on knowing the population information. And so only uses Z test if population standard deviation is known and you can read it from the problem and then rely on it. A T test gives you a worse p-value, so it's going to be larger. Again, the smaller the p-value, the better off we are, but it's when population standard deviation is unknown. And so then you have to rely on the sample standard deviation, the same sample that we collect to then reject or fail to reject. This is an important difference between z-test, but oftentimes it's more practical. To reiterate the point, these hypothesis testing, the whole goal is to prove the population mean wrong, that it's changed in some way. And so if that change or the population has changed, then oftentimes the population standard deviation is unreliable as well. Again, this is in contrast to confidence intervals, which rely on that population information to build out a confidence interval, but we're not necessarily debunking or saying the population information is wrong. In fact, oftentimes we don't have access to it. And so it's us building an interval. Versus hypothesis testing, we're trying to say, look, the old way, the hypothesis about the population mean is wrong, it's changed. And so oftentimes we simply assume where it's better to not use that population information and use a t-test instead. As a very little side note, I'll tell you that the distinction between Z and T differs sometimes between different textbooks or how you're going to differentiate between them. Oftentimes, these two is actually a combination between how big your sample is. If you have N less than 30, then you should use a t-test. If you have N greater than or equal to 30, you should use a z-test. And the population sample standard deviation ignored. Sometimes there's a combination between those two. So I just wanted to let you know, sometimes there is a bit more of a distinction between these two, but for us, we have a simple choice. Population standard deviation known, z-test. Unknown, t-test. And that's the distinction between our two tests. Speaking of those tests, we need to compute a p-value. Similar to before, there's actually many ways to calculate the p-value. You could use a calculator, you could use statistical languages like R, Python, if you want to import in a library. For Excel, there's different ways to compute it as well. This is one way, and then I'll show you maybe a more convenient calculator template that I've made for our convenience. So in order to conduct a t-test, we need 4 ingredients. The first 2 are sample information. I need my best guess, my evidence, my sample mean, and my sample size. How meaningful was this sample mean? Did I talk to 4 individuals or did I talk to 400 people? That's going to weight my sample mean. I then need my previous population information. I'll call this number 4, and here's why. Because I need 1/3 piece of sample information. I need to know the spread. And this is the one thing that's different from a z-test, because normally this is sigma, this is population, but not in this case. And so now I have the 4 ingredients. And again, that should be in the example that you read. Sometimes it might get confusing, sample versus population. But once we compute those, well, now it's off to the races to compute a test statistic. And this is similar to a z-score or a standard value. In fact, the formula is exactly the same. The only reason we call it a test statistic, a t, is because that's the distribution that we're using. But the formula, if you look, is almost the same as to a z. In fact, the only thing you need to change is population standard deviation. But since it's a sample, we focus on a t test statistic, kind of like a z-score tells you a position, relative position. And then we need a degrees of freedom based on the sample size minus 1. If you can compute these 2 ingredients and you understand the claim that's being made, maybe our claim is that the mean is less than 15. All right, if that's your claim, well, that's going to dictate you over here how you compute your p-value. Again, this does not rely on the null distribution. This relies on the student t distribution. And so to calculate that p-value, again, if you were going to do it kind of by hand in Excel, it'd be t dot distribution, that test statistic you computed, the degrees of freedom, or n minus 1, and then lastly, a 1. And you can see these other 2 here. Let me talk real quickly about them, though, because I think it's interesting. In hypothesis testing, we're often interested in a tailed study. And by tailed, I mean, in fact, that's what RT and 2C stand for. These claims actually refer to, this is less than 15, meaning I'm trying to look for values that are smaller, meaning that this is a left-tailed hypothesis test. If you're trying to find values that are greater than, like over here, then this is called a right-tailed study, hence the RT. If we're in both directions, the left and the right tail, then we simply call that a 2-tailed hypothesis test. And so that's what this abbreviation for. You don't need that, but I think it's beneficial to understand why we use this RT and 2T business. Like I said, this is not the main way we do hypothesis tests. It is a way you can compute using Excel. Instead, we'll rely on a calculator template as shown here. We did this previously, but as a little PSA, I'll tell you, if you go to Modules tab or you maybe look in Assignments, you should be able to find this hypothesis test template calculator. And it should look something like this. Where look, we had a z-test. We talked about that one earlier, where I generate a z statistic, and we have a t-test, where I gather another test statistic, but a t. And notice the inputs are very similar. In fact, the only thing that's different between them is one gives me population standard deviation entered in, and one is sample standard deviation. So it should be a nice little hint as which test to use, which ingredients do you have. Let's see some examples. A major car manufacturer wants to test a new engine to determine whether it meets new air pollution standards. The mean emissions, mu, of all engines of this type must be less than 20 parts per million of carbon, ppm for short. 10 engines are manufactured for testing purposes, and the emission levels of each is determined. The data, in parts per million, are listed in the table. Answer the following questions to determine if the new engine design can progress beyond the R&D and into manufacturing. All right, we have this new design, this new engine, and they're like, hey, look, I think this is good. You know, it's going to maybe save us some money to produce. Maybe we're producing a better product. Maybe we can charge more. But in order to start producing, we have to be below this threshold, this emissions standard, less than 20 parts per million. And so they say, okay, well, let's produce some engines and let's see what we have here. And out of the 10 engines, it looks like, ooh, this one's golden here. 15.6 parts per million. Uh-oh, we got some trouble though. This one's 20.5, just above that emission standards. 1 or 2 cars isn't a big deal, so long as the majority that we're producing pass inspection, or at least this pollution standard. And then if there's a couple that fail, then maybe we can pull those back, or we can simply hold them and clean them up and then try to put them out again. So we're looking at an average. Let's see if we can push these engines into manufacturing. Let's state the hypotheses. The first one is the null hypothesis, the status quo. They're talking a lot about averages or means, and so I know this is going to be a mean. Again, the null hypothesis is always going to be equal to, and our standard, it looks like it's 20 parts per million. So I should say the mean is equal to 20. And if you want to give it some units, we can say ppm for parts per million carbon. For our claim over here, what do we want to show or want to prove? Well, the framework should be the mean and 20. And over here, we're fingers crossed that the mean of our particular engine is less than 20. And so it's assumed, really, that the mean is greater than or equal to, it fails inspection, but what we're trying to show is that it's less than, so then we can justify manufacturing and building this engine. To test the hypothesis above, should one use a Z or a T test to justify your response? You'll remember that the distinction between these is just population standard deviation is known versus population standard deviation is unknown. As you go up top and you start to read the example, we'll say population standard deviation is unknown. And so it's going to require us to use a t-test. And that's the rationale, the reasoning behind it. Summarize the sample data by computing the sample mean, or X bar. For Excel, that's going to give us the average function. So I'll write in average. Again, I'll write like you would type. If you'd like, you can try opening up Excel, copy this data over and see if you get the same result. Average, the cell selection should be up top. It's always cell, cell. It should be A1 all the way to E2. And that'll give me my average here of 18.2. And again, that's parts per million. Ooh, you should see that number. We should be getting a little excited because our goal is to get less than 20. Ooh, and it looks like some good evidence, or maybe it is. Certainly evidence in favor of our less than, but it may or may not be significant. Let's find out. Calculate the standard deviation of the data equals to, we had a function, it was STDEV, and there were two options. There was .s and .p for statistic or parameter, or you can think about it sample and population. In this case, we're generating a statistic, or we're pulling it from a sample. Cell selection is the same, A1 to E2. And we get our sample standard deviation of 3.54. There we go. There's our spread. So we've summarized our data. Based on the sample mean computed above, can you confirm that all manufactured engines will, on average, meet the pollution standards? This idea, average and average, we had a sample mean of 18.2, and ideally this is pretty darn close to the population mean, which we don't know. Close. But how close? That is, well, it's actually a different job. I can't compare directly the sample and the population, and so the short answer is no. And again, because sample is not population. And so again, they're close, they're related, but I cannot directly take a sample and infer it onto a population. There needs a little bit of math, a little bit of statistics onto how we compare those. Let's actually conduct the test. Calculate the test statistic and p-value of the test. We have a couple inputs to put in, and then look at that. We've already generated our values. The first one is the initial mean. Again, this is the null. What has always been the status quo mean here is 20 parts per million. The sample mean that we collected was 18.2. The sample standard deviation was 3.54. For n, the sample size was 10. And if you want to be fancy, we can fill in, that was a t-test up above. Don't need to, but we can certainly be fancy. The test statistic is negative 1.6, which usually is a pretty good number for us, 0.79. Because again, this test statistic tells you how many standard deviations you are away from the mean. Normally, we like to see plus or minus 2, that we're pretty far away, 2 standard deviations away from the mean. We'll see if this negative 1.6 is statistically significant. To pick a p-value, you have 3 different choices here, all based on our claim. We said that we were looking for less than, and so that p-value should be 0.0712. Or I'd encourage you to write it as a percent. That should be roughly 7.1%. That'll make the comparisons more friendly as we progress. Speaking of the comparison, with a level of significance of 10% or 0.1, does the data support the claim? Justify your response. Anytime you're trying to make an inference, it's just based on a comparison of p and alpha. P is 7.1%. Alpha looks like it's 10%. Ooh, and if you're getting excited, that is a great thing because p is less than alpha. Again, happy days. I get to reject the null hypothesis and accept our alternative hypothesis, our claim, which is what we set out to do. Fantastic. How does that relate to supporting the claim? Well, again, to support the claim or the data, this is talking about the sample mean. The X bar we got was 18.2. Does this 18.2 support the claim? that the mean is less than 20, the layman might look at that and say, oh yeah, of course it does. But we could be more rigorous in that we can conduct a test to determine how significant the difference between these are. And that's what this p-value does for us, 7%. But that 7% is simply a likelihood that both of these things are true at the same time, that I get a sample mean less than 18.2 and the status quo is also true, equal to 20. And it looks like not very likely, but we need to set a threshold for what we consider to be unlikely. That threshold is right here at 10%. They say, look, if you're less than 10%, I'm going to consider that statistically significant. I'm going to consider that unlikely. And certainly we are below that threshold. We support our claim. Fantastic. Again, this is office parties all the way around. We're trying to produce this engine or manufacture it, and we've passed the first stage. We successfully are under that average. So then, what assertions or lack thereof can we state with a level of significance of 10%? Again, this is a happy statement. I get to make an assertion. It should look like this. I'll say, with 10% level of significance, we can assert that the mean engine emissions are less than 20 parts per million. And we have our statement. Again, whenever you're writing these statements, sometimes we can get lost in the weeds. We always need to make sure we have these two ingredients, the level of significance and also your claim. HA. You might write a different statement. It might look a little different, right? Your word choice, but we should always have these two ingredients. 10% level of significance, how confident am I making this decision, and what the actual claim is. And then, of course, if it's positive, meaning that we can actually make an assertion, we should state that we can make this assertion. And this is good for us. That means we can start producing this engine. However, notice that level of significance oftentimes isn't up to the manufacturer. It's up to the regulators. Here we go. In order to manufacture cars in California, a company must prove that they meet emission standards, that is, the mean carbon in parts per million must be less than 20, with a 5% chance their assertion is incorrect. Again, 5% chance that they're wrong. That's exactly what a level of significance is. Can this manufacturer begin producing this new engine design for their factory in California? Whenever we're making decisions, again, it's always that P and alpha comparison. From before, that P value was 7.1%. Alpha now is 5%. We're being a little bit more rigorous. Unfortunately, that level of rigor is going to have to change our opinion. This means we have to fail to reject the null hypothesis. Bummer. And for us, that means that these engines, we can't certify. We can't put a nice sticker on there and say, yep, they meet emission standards. And so in trying to produce in California with these more strict requirements, 5% level of significance, no, don't even think about it. And so because of that more strict level of significance, we are unable to produce engines, or at least produce this particular engine in California. But don't worry, it's not a complete loss. Maybe there's something else that we can do to get a more favorable prediction on our emissions. For instance, how can you estimate the true population mean for this new engine? Again, all we have is the sample mean is equal to 18.2. Is there something we can do with this to help predict the population mean, which we actually don't know what it is? Well, in fact, yes, there is. In fact, that's exactly what confidence intervals do. Confidence intervals take sample information and help build an estimate or prediction on the population mean. So let's try an example. Construct a 95% confidence interval for the true population mean. Whenever you hear confidence interval, I'd encourage you to write out the structure. We're dealing with a population mean, and so it should be that our mean is in x bar minus my margin of error, x bar plus my margin of error, where I have my left and my right endpoints. For the left, that's x bar minus my margin of error, then equal the sample mean we have up top is 18.2 minus, for the margin of error, don't worry, it's over here. I can write it equals, I should write confidence dot t, because we're doing a t-test. And then I have 3 inputs to put in here. The first one is 1 minus beta, my level of confidence. That should be 0.95, comma. 2, I have my standard deviation, in which case this is my sample standard deviation, 3.54. And then my last input is always the most friendly. It's just my sample size. We built or produced 10 engines to sample. And so here we go. This is my margin of error. Again, I encourage you to type out Excel, see if you can get the same answer as well. So it should be 18.2 minus 2.5. And we should get 15.7. That's parts per million. On the right, that's going to be X bar plus my margin of error is 18.2 plus 2.5. And that's going to give us 20.7 parts per million. And so my confidence interval could be as low as 15.7, and that's parts per million, and as high as 20.7 parts per million. To make a comparison for us, again, this was a 95% confidence, a beta value, and notice that our confidence interval is above that 20 threshold of these emission standards. And so both the 95% confidence and alpha level of 5%, they have the same conclusion that both of these say that, look, the mean is not below 20. Because again, this population mean can be anywhere inside of here. It could be as low as 15.7, could be as high as 20.7, and could be literally anything in between there. It's all equally likely to occur. And so hypothesis and confidence interval come to a very similar conclusion. They just do it in a different way. A company often wants to underestimate its emissions to improve their image to customers. What is the minimum average of emissions this company can claim with 95% confidence? They can say, look, our emissions are as small as mu is equal to 15.7 parts per million. There are a lot of ways to try to mislead with statistics, and this is certainly one. They can say, hey, look, with 95% confidence, our mean can be as small as 15.7. In which case, if Elena read that, they go, hey, look, that standard was 20, and they're pretty well below that at 15.7. But we know better. Okay, we know that this is just a very charitable pick from their confidence interval. It could be as high as 27. In fact, it's equally likely to be that low that it is to be 20.7 that high. And so this is something to watch out for when we do these claims, to pick apart, hey, look, this is your claim, but where's that coming from? In which case, it's being very charitable for what they can claim the smallest their mean could possibly be. Next example. A locally owned independent department store has chosen its marketing strategies for many years under their assumption that the mean amount spent by each shopper in the store is $100. A newly hired store manager claims that the current mean is higher and wants to change this marketing scheme accordingly. A group of 27 shoppers is chosen at random and found that they have spent a mean of $104.93 with a standard deviation of $9.07. Assume that the population standard deviation of amount spent is normal. Interesting. Clearly state the hypotheses. What's our status quo? What has it always been? The null. They're talking a lot about means over here, and this is a mean is equal to, that's always the structure for the null hypothesis. Notice up top, we have $100 and then we have 104. But notice this mean is found from the sample. So if you want to help give some context, you can write X bar here. But this mean average is for the population. Everybody spends this much. So you can write 100. If you want to give it some context, you can give a little dollar sign there. For our claim, this is what we want to show. It's that the mean we think is greater than. The manager claims that the mean is higher, because that's what we're trying to prove. Greater than 100. And again, you can give it some dollar signs there to help bolster your claim. To test this hypothesis, should one use a Z or T test? Again, the game here is just, do we know the population standard deviation? Population standard deviation, is it known or unknown? We have a standard deviation here of 9.07, but notice this comes from the sample. This should be abbreviated S. So the population standard deviation is unknown. T-test. Let's say an intern conducted the test that we suggested above and finds a p-value of 0.0108, or about 1%. Does this p-value give strong evidence to reject the null hypothesis? Justify your response. Again, our little notion here was the smaller the p-value, the better. Our rule of thumb was that alpha was 5%. That was a nice rule of thumb, a standard out there. And yeah, we're quite a bit less than that. This p-value indicates some strong evidence that that sample that we gathered of $104.93 is strong evidence to reject that status quo. Let's actually get to it. With 5% level significance, does this test confirm the manager's claim? If so, what is the claim? So again, whenever we're making decisions, it's always comparing P and alpha. Looks up top is 1% and alpha is 5%. Fantastic. It is less than. Again, happy days for us. It means we get to reject the null hypothesis. And here's the important part, and that's to accept the alternative hypothesis, or that's the claim. Does this test confirm the mayor's claim? Yes. Yes, it does. And what is that claim? The claim is that the mean is greater than $100. This is the claim. So again, the manager shouldn't go out there and say, hey, look, the average is $104, $105. This is not equal to the population mean. All that is anecdotal evidence to suggest that it's greater. If we want to actually get an idea for what the population mean is, that's where confidence intervals come into play. But certainly we should not use our anecdotal evidence solely. Next example. A company produces ball bearings which have a mean diameter of 5 millimeters. After replacing some parts in their production line, the lead engineer wants to check to see if there has been a change in the diameters of the ball bearings being produced. Assume that a sample of 12 ball bearings are checked, resulting in a sample mean of 5.04 millimeters with a standard deviation of 0.07. Clearly state the hypotheses. Again, we have some ball bearings being produced, and this is their advertising. They're saying, look, these things are 5 millimeters, and they're golden. We're not deviating from that. But after replacing the parts, they're like, I think that there maybe has been a change in the diameter. The null hypothesis is the status quo. Again, don't worry about it. In this case, we're talking about a mean, always equal for a null hypothesis, and 5 millimeters. The mean is 5 millimeters. Again, if I get some units, we can do so here. Next up, I'm doing the claim. Well, the claim should have the same framework, the mean of 5 millimeters, but now I'm interested in what kind of change, either less than, greater than, or in this case, there's been a change. We're not sure which kind. We'll just write not equal to. We don't have to be picky here. We just think there's a change. Should we use a z-test or a t-test, and why? This is always related to the population, standard, deviation, or whether you know it or not. So I'd encourage you, read up top. In fact, it says plainly here, sample standard deviation S. So a population standard deviation unknown, we are forced to use the worst, gives us a worst p-value. And so it's always preferred to use a z, but oftentimes we can't do it. T-test. And we have a list of values to plug in here. The first one is the initial mean up top. That's 5 millimeters, or at 5 there. The sample mean that we conducted was 5.04. The sample standard deviation was 0.07, small spread. And in our sample size, we only gathered 12 ball bearings for the test. The test statistic we can see over here. In fact, if you want to be fancy, you can write in T. This is technically a t-test statistic of 1.9795, which should give us some hope. That's a great test statistic. Usually plus or minus 2 is what we're interested in. It may not help us though. Let's see. Find the p-value. For us, we were stating not equal to, which gives us actually a wider bandwidth. It's going to give us a higher probability. That should be 0.0733. Or if you want to think about that in percent, you can write 7.3%. Would you reject the null hypothesis at alpha equal to 10% level significance? Whenever making these comparisons, I have my P, I have my alpha. P was 7.3%. Alpha here is 10%. Ooh, you're getting elated because P is less than alpha. Fantastic. I get to reject the null hypothesis and accept the alternative hypothesis. Fantastic. And again, if they're asking, hey, what's your reasoning? How do you know that? Boop. It's right there, just in that comparison. But here to really get into producing a statement from your decision above, write a conclusion statement or lack thereof. Again, the whole reason we have these two is a little hint that if you fail to reject, there's not really a strong assertion you can make. Regardless of the way you're writing your statement, though, we should always include these two ingredients, the level of significance and our claim. And we'll write it like this. I'll say with 10% level of significance, we can assert that the mean diameter is not 5 millimeters. That engineers' suspicions, right? When we're looking at those ball bearings being produced, we replace these new parts. Well, we can confirm with 10% level of significance, that's my level of certainty, that, yeah, correct, the mean is not 5 millimeters. Okay, make sure you always include those two ingredients. But say maybe before you halt production, right, you say, everybody, leave for the day, we're not going to be making money today. We want to be very sure that if we hold production line, that it's worthwhile. So we want to be a bit more strict. With a level of significance of 5%, does the data support the claim? Circle and justify your answer. Again, these decisions, reject, support, are always based on P and alpha. My p-value is 7.3%. Alpha now is a little bit more strict, 5%. You're getting worried. It's an accurate feeling. It's not a good feeling because this is a failure. Bummer. P is greater than alpha. That's fail to reject. I am unable to say bump the status quo. Our claim is correct. Whenever we're trying to make this decision, it means this sample we collected, the X bar equal to 5.04, it didn't provide us strong enough evidence to reject. We failed to do so. So this sample, 5.04, does not support the claim. Again, it might have seemed good because it was different, but apparently not different enough. And so I'd encourage you to associate do not support with fail to reject. That's the null hypothesis. And support being a good thing, meaning I get to reject the null hypothesis. Unfortunately for us in this case, when we increase that level of rigor to 5% level of significance, can't do it. What assertions or lack thereof can we state with the level of significance of 5%? This is the embarrassing part. We did all this work and we're like, hey, we have a suspicion. Let me take some of these ball bearings and measure them. I got my calipers out. I made a little table. After all that work, what assertions can I make? The short answer is none. I'll say this. I'll say with alpha equal to 5%, we cannot assert a change in the mean diameter. Five millimeters. We cannot assert a change in the diameter. Again, there are many ways to write these statements. We should make sure we always have those two ingredients. Level of significance, got it over here. And then maybe I wrote it a bit differently. But mean change, 5 millimeters. We cannot assert. We have those two ingredients and you're golden. You know what this bottom statement is? It's a very fancy way to say nothing at all. And that's really how these hypothesis tests go. It's high stakes. Unlike for confidence intervals where we can simply build a range and I can say, hey, look, it's somewhere in this range. And sometimes we can be charitable and pull from the smaller means. Hypothesis testing are really pass or fail mentality that, look, if I get to make a statement, ooh, it's a big statement. Everybody stop the production line. We're pulling out these machines. We're checking to see why these things are being produced appropriately. Or complete and utter failure to say, look, I was having this suspicion, but it's unconfirmed. Don't worry about it. And so let me recap and wrap with this. It's because of that difference that hypothesis testing is high stakes. It's kind of a pass or a fail mentality that we often prefer hypothesis testing versus confidence intervals, because confidence intervals give you a range of values. And then from that, you infer this pass or fail versus hypothesis testing. That's all they're meant to do, is to quickly tell you, okay, stop the line. These things are not being produced correctly. Or, hey, you know what? Suspicion, unconfirmed. Keep doing business as normal. And then maybe the next day they can take another sample and they can say, is everything still being produced appropriately? Good, keep producing. And so these hypothesis testing are a quick way to simply do that check instead of having to build a confidence interval where we have to interpret. Hypothesis testing much more quickly address that change. Look, if you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.